So this and the next slide are just a short overview on San Andreas Fault, which is probably the world's most famous fault. This fault is located in California. It splits the westernmost part of it from the rest of California, as you're seeing in the little map to the right. What is happening in this case is that the Pacific Plate, which contains a bit of the continental mass that is currently attached to North America, is moving northwest relative to the North American plate. So that's what you're seeing right here. Pacific Plate is moving northwest relative to the North American plate. So the size of the fault segments and through which some of the displacement has been recorded are of 100 to 200 kilometer segments. So there's one segment right here basically on the northern part, another segment down here in the middle, and then another one here in the southern part. And in each of them, some sort of displacement has been recorded. So some of the segments within this fault slide smoothly past each other. So even some of the subsegments, I should say. So for example, here, it might move a little bit smoother than in areas like this, even though they're both in the central part of the fault. So in this case, this is called fault creep, when there is a smooth passing between two different locations. But at some other segments of the fault, it may function like a mechanism like the one we saw in the last slide, where you have a lot of stress building up. You have that frictional resistance kind of acting up so that there is no slippage. And suddenly when the energy is too great, the stress is too great, I should say, the energy is released in a very large movement, in a very large event, as the earthquake is. So there are areas where there is some extra stress, and they act usually as if though they were sticking to each other. Such areas have been forecasted to slip every 50 to 200 years within the San Andreas Fault. And by some laser measurements that have been done, the stress that builds up within these more sticky areas is between 2 centimeters to 5 centimeters per year. So in the sticky areas, there is an offset of about 1 to 4 meters every 100 years or so. So every 100 years, a section that used to be right here is now 4 meters, a little bit to the northwest relative to the other area over here. So there are certain trends that are seen due to this San Andreas Fault's movement in terms of experienced earthquakes within California. So the first recorded and greatest earthquake to consider here in California due to the San Andreas Fault movement was the Great Earthquake of 1906. So we've already talked a little bit about this, but this happened in San Francisco, or near that area. The displacement that occurred due to this great earthquake was of 4 meters on average, but some of the sections slipped about 9.6 meters, I think. So in the city, about 3,000 people died, mostly due to the fires caused by the rupturing of the power lines and by the large number of wood houses that existed. So all these breaking of the power lines and wood combined made for a lot of fires within the city. The next easy to associate spot was the one in Loma Prieta in 1989. So this earthquake was of magnitude 7 or so in the Richter scale, and we'll talk about this scale later within the lecture. But basically, although that magnitude is not necessarily very large, it was still very costly in terms of the amount of lives that were lost. So about 63 people died within this earthquake of 1989 in Loma Prieta. Then another earthquake in 1994 in Northridge, which is near LA, happened. This earthquake was of magnitude 6.7, and it caused 57 deaths. So overall, granted, the amount of deaths that an earthquake causes is highly dependent on the population near the area, to how populated the area is, also based on the infrastructure that is around, on the specific soil type, on the building materials that are used, on the measures for mitigation. But it is definitely undeniable that this fault, so San Andreas fault, that is very, very long, as you saw in the map in the last slide, has been active and has been slipping at a very fast rate in terms of geological terms. All right, so moving a little bit afar from San Andreas fault and coming back to earthquake dynamics. So typically, strong earthquakes are followed by numerous earthquakes of lesser magnitude. These lesser magnitude earthquakes are called aftershocks. So these usually result from the adjustment of the crust along the fault surface after the initial greatest part of the slippage of that shock. So they will typically diminish both in frequency and in intensity over a period of several months after the initial earthquake. For example, in the 2010 earthquake of magnitude 7 that happened in Haiti, which took many, many lives and caused a lot of destruction to the infrastructure of the area, there was detection of about 60 aftershocks, all of magnitudes greater than 4.5. So obviously, these aftershocks helped inflict further damage upon the structures, which in turn took many of the lives. And again, these were just 60 aftershocks recorded that were of greater magnitudes than 4.5. Hundreds of other earthquakes of relatively smaller magnitudes were also recorded after this great earthquake of Haiti. So, although typically the aftershocks tend to be smaller, they do trigger the destruction of some already weakened structures that were weakened by the initial main shock, like it happened in Haiti. Or like it happened, for example, in the Armenia earthquake of 1988, which had a magnitude of 6.9, with aftershocks of 5.8. So, in contrast to aftershocks, foreshocks are smaller than the earthquake, so usually they tend to have lesser magnitude, and these are these are movements of the Earth that happen before the main shock. So they precede the major earthquake usually by days and in some cases by years. So the monitoring of foreshocks is, for example, a strategy that is used in the forecast of earthquakes, and we will see that later within the lecture. However, it is not very good at predicting them, simply at kind of knowing that there may be some further greater activity in the area. So it's not one of the best methods to predict earthquakes. So, I should also mention that foreshocks sometimes do occur before the main shock hits, but sometimes they are not present at all. So many times they won't appear before the main shock. Okay, so now we move on to faults and large earthquakes. So the first fault type that we're going to see is thrust faults. But overall, the slippage that does occur along faults can be explained by plate tectonics, which I'm sure is not a surprise to you, as said theory controls so many of the geological processes that we've already seen during our class time. So, as the lithospheric plates grind past one another, they typically interact with each other in three main ways. So these three are associated with the three main types of plate boundaries, which is also not a surprise. So the first way in which this grinding of the two blocks takes place, the two plates takes place, is at convergent plate boundaries. So in this case, the two plates come into contact with one another. This type of boundary is responsible for causing the strongest earthquakes. So when these convergent boundaries occur, compressional forces, which are associated with, again, some sort of collision, will slice the Earth's crust along numerous large thrust faults. Okay, so this is what a thrust fault kind of looks like. So this type of faulting caused by the earthquake is for example, the one that is seen in the Himalayas. So this type of faulting caused the earthquake seen in Nepal in 2015, which we've already talked about a little bit. So again, this earthquake happened a little bit north of Kathmandu, which is the capital of Nepal, and it caused a lot of damage to the economy and to the amount of lives lost into the infrastructure. It also is one that caused, for example, the major earthquakes that are seen in Peru and Chile, for example. So many of the earthquakes that we're seeing in the Andes are due to the convergence of the Nazca plate with the South American plate. So there's a mega thrust taking place right here in this area. And I'll explain what a mega thrust is in a second. So in this type of thrust faults, which occur when there is some sort of separation between the subducting slab of oceanic lithosphere and the overlying continental lithospheric plate, right here, so the separation of the subducting slab and the overlying plate, there is an extensive fault zone that results. So this fault zone that results from that separation is called the megathrust fault. So because it is so large and so damaging, I think that that's why they call it the megathrust fault. So megathrust faults can measure to be several thousands of kilometers in length, like you're seeing here in the Andes. And it is, or I should say, just a little bit west of the Andes. And it is megathrusts that typically produce the largest earthquakes that are recorded. So earthquakes like the 2011 earthquake in Japan was caused by a megathrust earthquake. The one of magnitude 9.5 in Chile in 1960 was caused by a megathrust earthquake. The one in Alaska in 1964 of magnitude 9.2 was also caused by a megathrust earthquake. So definitely thrust faults tend to cause earthquakes that are the most damaging and the greatest ones. So divergent plate boundaries are typically associated with faulting. This type of faulting is relatively shallow. So although the faults that are caused by this boundary type tend to be smaller, so the earthquakes tend to be of lesser magnitude, they cause mostly surface earthquakes, okay, so near the surface. The fault type that is associated with divergent plate boundaries is called normal faults. However, normal faults can also occur by other processes, not just by divergent plate boundaries themselves. For example, in the Basin and Range Province, which is in Nevada, Eastern Oregon, southern Idaho, and parts of the surrounding states of Nevada, the continental lithosphere of the North American plate has been stretched towards the west mostly as the Pacific plate continues to move northwest. So this stretching has caused many normal faults. And because parts of the Earth are moving away from each other, then you have that stretching that occurs. So one of the most recent normal faults came from the earthquake of 1983 that displaced basically, or it made the Lost River Valley subside about 3 meters. So the picture that you're seeing on the bottom right here is one of the students of last year's class from the field methods class as she's standing in front of the fault scarp caused by the earthquake of 1983 there in the Lost River Range near Mount Bora. Okay, so one important way to distinguish whether a fault is normal versus thrust is by looking at the behavior of one block versus the other. And we'll do that in the next slide in 1 second. Before I do this, I did want to show you the video of, there you go, of the plate's movement and how that stretching took place as the Pacific plate is moving northwest and stretching that western part of the North American plate. So you're seeing that stretching ongoing in Nevada, in Oregon, and in Idaho.